saying that's difficult. They're saying it's difficult.
Are you looking at? Oh no, I'm studying for using Word. Did you guys understand the chip? I mean, I don't know. You're just gonna say questions on
No, no, I'm talking about today.
Oh, no, we are talking about the class for work and we need to separate it in theory, so we are just doing is like writing our names before the class.
No, I mean, the 2 weeks, we have to download the 2
Well,
Excel.
I think it's
Really?
available.
Okay, I didn't check that.
These are.
So like he's also saying that we need to download the Python. Download the Python.
I have students teaching.
Yeah,
Yeah, I'm going to go to this.
Oh, today's class, okay, I was thinking about Tuesdays.
Yeah, no.
Oh, yeah, you're.
Let me.
2 Excel.
Yeah, that's why I don't want to do it for you. Is it not solid 87? But we can check it. It's really early to start.
Just wondering, I'm not sure, but maybe as middle of November, I can come to you to the class.
Risk management.
How would it be
And
possible
anywhere
to record this?
Middle of November.
Yeah. Or like which day? Actually, I think the 12th.
Yeah. Can send me an email.
Sure.
I'm not sure yet, but I will.
Yeah.
Just
And also-
send me an email on Tuesday.
And maybe also the bottom software, I'm not sure about the thing.
Yeah.
Yeah, send me an email.
When I
And
take
then it
three
will be
weeks
possible.
summer and green fall, then I'll just finish in the second spring. But if I take 2 weeks summer, do another semester.
I will send you through WhatsApp.
Okay.
I think everyone did 3.
Okay, so first I think I made an announcement on Husky City already. So the final exam will be in person in this room from 6 to 9 on December 3rd, which is a Wednesday after Thanksgiving week. So we have four, if we include in this week, there are 4 more weeks. I'll finish historical simulation, and then we will talk about Basel. We'll spend like 2 weeks on Basel 1, 2, 3, which is a framework for bank regulation. And then in the last week, which is the week before Thanksgiving, we will have a final review. And then we will have final exam after Thanksgiving. Yes.
May we have the cheat sheet on the final review day, so we can have a look at.
Yeah, we will. There is going to be a formula sheet. I will post the formula sheet in the week before. Which event? Oh, I think I made an announcement last week. Is it in store?
Yeah.
Yeah, I think that, yeah.
Professor,
Yeah.
are we going to have like graphics exam before the final?
No. The exam problems are, I'll talk more about the exam in the week before the Thanksgiving. So the questions are going to be very close to the questions in your homework. Yes?
Is there going to be a formula sheet provided?
Yeah. So I explained that I'll provide a formula sheet so you don't have to memorize all the formulas.
Will you be able to upload that on Husky CT?
Yeah. I will post it before Thanksgiving.
Okay.
Yeah.
When we gonna have like the third assignment homework?
I'll have to check that, yeah. I'll have to check that. Any other questions? Okay, let's, we don't have much.
Excuse me.
Yes.
So is the exam like really gonna be based off of the problems we do on the homework?
Yeah, homework and those questions in on my slides.
Okay.
So there are going to be 2 parts. The first part are going to be multiple choices, and the second part is mainly about some numerical problems. But I'll talk more about details about the exam in the week after, before the Thanksgiving. Okay. So last week we talked about these 2 formulas, which can be used to estimate the value of risk and expect shortfall if the loss of a portfolio follows a normal distribution. And we're going to talk about 2 approaches to estimate VAR in practice. One is to use one is called historical simulation, which is going to be the main focus of today's lecture. The other one is called model building approach. The model building approach is pretty straightforward. It's basically we only focus on this model which assumes a normal distribution. Therefore, it's mainly about applying these 2 equations. In historical simulation, it's slightly different. We don't make assumption about the distribution of your loss. Okay, we will look at that later. I think we went through those examples. Now, if you want to use these formulas for longer term horizon, instead of by long-term horizon, I mean you look at the value at risk at, for example, 3 days, 10 days, instead of 1 day VAR, estimating 1 day VAR. In the longer term, obviously your loss is going to be, your risk is going to be higher because you're going to hold that portfolio for longer term, right? So we also have a formula that you can use. If we make assumption that the loss over this successive days are independent, we can use these two formulas. So you first estimate the one-day VAR using our previous formula. Well, you have to be careful here. If you estimate one-day VAR, mu and sigma, these parameters has to be one day, okay, 2. So your expected loss in a day, which is kind of close to 0. And more important is the volatility. This has to be, this standard deviation sigma has to be one day sigma. Now, this reminds me of something important that I'm surprised that many people have no idea how to convert volatility over horizons. So a pretty straightforward question. If the SP 500 volatility is 16%, how do you compute monthly volatility? So
16% over what time period? A year?
annual, yeah. Okay. That's correct. Now the question is, what's the monthly vol? I'm surprised that many students don't know how to convert this, but I think this is.
Would you just take the 16% and divide it by the square root of 12?
Yeah, thank you. So it should be 16% divided by the square root of 12, which is I'm not sure. You can do the calculation yourself. Okay? How about the daily volatility?
They usually do the square root of 256.
Yeah, you can use 52 weeks. 52 weeks usually is the number of trading week in a year and 5 days a week. So that's kind of like 260. But you have to be careful, right? For different, there is no single number that people use. Different people use different number of days in the year, different data, or different resources, different sources. So you have to check the manual of those. But usually this seems to be a reasonable number, 260. So now if I give you, for example, you want to count, if you have an SP 500 portfolio holding an SP 500, your one-day VAR, if you want to estimate one-day VAR, you have to use daily volatility. If you use annual volatility, that is wrong, okay? So you have to first convert it to daily volatility, which is 60% divided by square root of 260, and then that's just the volatility. Volatility is the standard deviation of return, so if you need to use this formula, this sigma is not the volatility, it's the standard deviation of your loss. So if you have to times it by the dollar value of your portfolio. Let's assume that it's $1 million. Okay, that is going to be your sigma when you use this formula. That's how you use this formula. So if you want to compute one-day VAR, you use the one-day daily volatility, and this formula is, these two formulas are very close to the formula that we use here to convert convert annual vol to daily vol because now you can see 1 day here, your P-day volatility is gonna be 1 day volatility times the square root of T. Okay. So you can see that, right? Annual volatility is daily volatility times square root the number of days in the year, which is 260. So that's how we obtain daily volatility from annual volatility. So these are the same formulas. But we have made a very important assumption, which is that the returns are independent. This is in generally true. But there is some, so this is just the example, just to save some time, I guess I think I post this the slides with the answer on Husky CT already, so you can check the answer. It's you just plug in the formula. That's it. Okay, times the square root of. So you basically use the 1 day vol and the VAR and expect shortfall times the square root of 3. You can obtain 3 day VAR and expect shortfall. Now, that's under those two formulas are under the assumption that the returns are independent over time, over days. But if you allow some autocorrelation basically means, so it's slightly different from correlation. We introduced the correlation at the beginning of the semester. It's basically the co-movement between two stocks in the same day. Autocorrelation is a correlation of return for a single stock over 2 days. So this is like timeline. So this is called autocorrelation. It's a correlation of return over time. Intuitively, I guess you can interpret it as like, if your autocorrelation is positive, which means that if the stock return today is high, the stock return tends to be high tomorrow too. That's a positive autocorrelation. Negative autocorrelation basically means if stock return is low today, stock return tends to be high tomorrow. That's negative autocorrelation. So that's what we mean by autocorrelation. So if you consider autocorrelation, which is measured by rho, you have to replace the square root in the previous equation with this equation, okay, to adjust for autocorrelation. So you can take a look at this table. The first row represents the case that there is no autocorrelation, so returns over days are independent. And then the lower rows include the second, third, and fourth, basically shows you that term, the adjustment term, when there is a positive autocorrelation. So, for example, if rho equals 2.2, which is a positive correlated return, you can see that the long-term VAR, like 250 days VAR, is going to significantly higher than the case of independence, zero autocorrelation. So if you use zero correlation, you probably underestimate your VAR. So this is another example. Basically, you're going to calculate the VAR, 3-day VAR inspection for when there is autocorrelation. Basically, you have to calculate this correction term. And so this autocorrelation is going to be matter for VAR inspection, for especially for the long-term horizon, long-term VAR inspection. If you underestimate autocorrelation, that may lead to underestimated VAR inspection. But as I said, in general, returns, if you look at the stock portfolio, stocks returns are independent, most in general. Generally speaking. So confidence level. Confidence level, when you estimate the VAR, you have to choose a confidence level. This is going to depend on the type of risks when you choose the confidence level. Like if you look at the regulation, regulators requires 99% for market risk, for the S&P 500, for example, and a 99.9 for credit and operational risk. So they have a higher confidence level requirements for credit and operational risk, and a slightly lower confidence level for market risk. And bank want to maintain a AA rating, must use confidence level as high as 99.97 for internal calculation, which means, right, so if you, VAR is 3 billion, with the 3 billion of equity, capital means equity, right? So most of this tier 1 capital, so it's 5 billion equity, you only have like 0.03% chance of becoming insolvent, which is very, very small. So that's how we use the confidence level. So you can basically set the confidence level to set the probability of default if you set the equity to be your VAR. Because VAR is the probability, VAR is the loss, that the probability of your portfolio loss greater than VAR is going to be less than 1 minus the confidence level. I think this is very important. I'm going to skip that. Okay, the last thing that I want to talk about is backtesting. This is a very important idea. What we do here is you want to test your estimate of VAR. So using some methods, there are a lot of methods that you can use. You're going to obtain a VAR. And now you want to test it to see if it's a good or bad estimate. We can use some historical data to test these estimates. This is called backtesting. VAR is very straightforward to test. So let's focus on VAR. The idea is pretty straightforward, so we're going to mainly talk about the idea here. So backtesting VAR involves looking at how often an exception occurs. So we're going to define the exception as an observation in which the loss is greater than VAR. What is the probability loss greater than VAR? According to definition. It should be y minus the x%, where x% is your confidence level. Right. So if you set your confidence level to be 99%, the probability loss greater than VAR is going to be 1%. Because this is how VAR is defined, right? So if you have x% VAR, probability loss less than VAR is going to be x%. So the probability loss greater than VAR is going to be y minus x percent. This is how we define VAR. So let's look at this example. Okay, so let's assume that 99% VAR. We estimate one-day VAR is $10 million. And then we have some historical data. So we're going to track the loss of your portfolio in that sample. And that sample covers 1,000 days. So you have 1,000 observations of the loss of your portfolio. How many days such a loss of the portfolio should be greater than 10 million? So how many exceptions should I expect?
What's 99% of 1,000 days, so 10?
10. Thank you. So because the probability that loss greater than VAR is going to be 1%, given that the confidence level is 99%. So, and I have 1,000 observations, 1% of 1,000 observation is 10. So I should expect 10 exceptions. And obviously, when you start to count the number of exceptions, it may not be exactly 10. It can be 9, it can be 8, it can be 20. But if you see, for example, if you found that there's like 8 or 9 exceptions, that's probably acceptable. If you found something like 20 or 30, that probably implies that the estimates is wrong. You have to adjust your estimates. So for example, if we found 15 exceptions, should we reject the VAR? That's so we need to find a rule here, basically. We need to find a rule to tell me that we have to, how many exceptions is not acceptable. Okay. So this process, this procedure is called hypothesis test in statistics. How do we reject the VAR? In order to scientifically come up with a boundary that if the number of exceptions is too many, then higher than this number, I will reject the VAR, and otherwise I won't. So I have to come up with a boundary. So this is what statisticians give us. So basically the number of exceptions is going to follow this distribution. It's called a binomial distribution. Okay. So looks complicated, but doesn't really matter. Just look at whenever you see a very complicated form of function, it doesn't really matter. You just focus on those unknowns, okay, or parameters, what we call the parameters. So here, let's look at this. So n here represents the total number of observations in your sample. In the previous case, it's 1,000. P is the probability of an exception. In the previous case, it's 1%. And M is the number of exceptions. Okay? K is just is not a parameter because K has to be equal to M to M, and then you take the sum. So K is not an input of this model. So you can forget about K. And I'm going to show you that there is a built-in function that you can use in Excel. This is a standard distribution, so you can just put N, P, and M in as an input of that function. You'll be able to get the probability. Okay. And more important is that if the probability of VAR is being 16M and more days is less than 5%, we can reject the VAR estimate. This is this is the rule. Okay, the 5% is the rule. We have this formula, and then we impose this 5% rule, which means it's very rare. This 5% basically means that, for example, if you find the number of exceptions is 15, and using the function, the distribution that you calculate, you can solve for the probability that number of exceptions greater or equal to 15. If you find it to be less than 5%, which means that the probability of observing 15 exceptions is very, very rare. So you can reject, which means you can reject the VAR. If you plot this, the probability density function of this binomial distribution, this is the probability density function, you can find that this is kind of like the boundary that you can come up with. Okay, the boundary is set so that the red area, which is the probability that the number of exceptions greater than this boundary, is 5%. This red area is 5%. Okay. So if you observe number of exceptions on the right-hand side of this boundary, then you can kind of reject the VAR estimates. Otherwise, you can accept it. So let's look at an example. Suppose that we backpass the VAR using 600 days of data. The VAR confidence level is 99%. What is my expected number of exceptions? 6. So if we observe 9, should we reject it? If we observe 12, what if we observe 12? So I'm going to show you this on Excel. Example, I have a number of exceptions, 9. Call it X. So I'm gonna use X to denote the number of exceptions that I found. The probability for any other, for the probability exceptions greater than the number of exceptions that I see observed is you can call this function. So let me see. So you're going to call this function called binomial distribution. So the number of exceptions, I'm going to use 8 because I want to calculate the probability the exceptions less than 9. So it's going to be from basically 0, 1, 2, 3, 4, 5, 6, and 8. So less than 9. Okay, so we're going to do this function is going to return the cumulative. You can see that the last parameter here is to call the cumulative function. So I'm going to use the cumulative function. That's why I use 8 for the first parameter, because I want to calculate the probability exceptions less than 9. Okay? So it's going to be cumulative probability from 0 to 8. And the number of observations is the second parameter, which is 600. P is the third parameter, which is the probability of exception. So that's going to be the probability of number of exceptions less than X. Now we can compute the probability exception is greater or equal to X. It's going to be Y minus it. So you get the probability the number of exceptions greater or equal to 9 is going to be about 15%, which is greater than 5. So we are not going to reject this VAR, but if you observe the number of exceptions to be 12, you will find that, sorry, B1 minus 1. Thank you. So you will see that the probability exceptions greater than 12 is going to be about 2%, which is less than 5%. So you are going to reject the VAR. Now the question, the last question is, if VAR is rejected, is the model over or underestimate VAR? Should you increase the VAR estimates or lower the VAR estimate?
It's underestimating it.
Yeah, you underestimate it, right? So the number of there are too many number of exceptions, so you have to raise the bar. You have to raise the VAR estimates. Therefore, the number of exceptions is going to go down. So you have to figure out a way to raise your VAR. You underestimate the VAR, the risk. So that's the back testing. Generally, the difficulty of backtesting of VAR increases, the confidence level increases, because if you increase the confidence level, it's going to be very rare to observe exception. Very few data points for exceptions, and when you want to test that, that will be very inaccurate. Okay, so we usually use a low level confidence level for VAR and back test purpose, and then use some kind of a theory to extrapolate the VAR estimates to the confidence level that is required. But the idea of this back testing is very, very important. This is just one application of this idea. Now, we're going to do historical simulation. As I explained in the beginning, there are two approaches to estimate VAR. One is historical simulation, and the other is the model building approach. In model building approach, you can you basically assume that loss follows a normal distribution, so you can use our formula. Now let's focus on the historical simulation. So this is a kind of a Monte Carlo simulation, if you ever heard about it, but it's not based on random number. We use historical data as kind of a random number generator. So because this is going to be some data work, so let's start with some standard. Let's do some warm-up exercise. So we're going to do something very standard. So we are going to solve for the daily return of SP 500 and the Financial Times 1100, and we're going to solve some mean and standard deviation. Going to calculate some correlation, and then we will talk about the idea of historical simulation. Let's start with this. I post these two spreadsheets on Husky City. The first one, the data, C20 data, and the name C20 data. There are two tabs. Now you can use your laptop, so open the file. The first one is called C12 data. There are two tabs. One is called stock, and the other is called FX. This represents the exchange rates between U.S. dollar and three other currencies. The stocks, the tabs under the tab stock, we have a sample starting from 2018 up to 2020 across these four indices. SP 500. This is an index, stock index in UK. This is stock index in France. Stock index in Japan. That's why we have these currencies, exchange rates, so that we can convert all of them to US dollar, to the same currency. And this number represents the level of the index. Now, there is another file. I would strongly recommend that after class you should try to, instead of just browsing my spreadsheet, I think you should try to create them yourself and see if you can replicate this file, all the tabs in this file, starting from the data file, the C20 data. Okay? So everything is based on the data, and I come up with these this analysis, the spreadsheet, the analysis file. So we're gonna do some warm up first. First of all, yes, we can. So since we haven't done any data work before, I guess we can start with these the two indices. This is how we compute the return on stocks. We kind of be careful here. I ignore the dividend. I should not. But, so this is how you compute daily return. So you have the, well, these are closing prices. Okay? So if you, for example, this is the closing price on May 9, 2018, and this is the closing price on May 10, 2018. So if you want to compute the return, stock return from the closing hour on 8th, from 9th to the closing hour on 10th, you can use the closing price on day 10 on 10th divided by the closing price on 9th and minus 1, or you can just okay. So, which is the same as on the my spreadsheet, or you can to be consistent with my spreadsheet file. So this is the formula. And yeah, in Excel, you can, I'm not sure if you, I guess many of you probably know this. There's this small dot on the lower right corner. If you double click that, you can apply this formula to all the rows. So you can obtain daily return for SP500 over the sample. That's how we compute the daily return. As I said, I ignored dividend. Dividend is tricky, so you have to be careful. If you know that if the data include dividend, you should include dividend as well. But I kind of ignored it. Now, if you compute the average daily return, I use 260. So we have the return on SP500 over the sample period, and we can calculate the average return over the sample period by selecting all the returns. That's going to give me an average daily return. You have to convert it to annual. So assuming that there are 260 days in a year, and if you want to report in percentage, you have to times it by 100. So over the sample period, the average return of SP500 was about 14%. Okay. That's and then you can compute the volatility, which is standard deviation. Select all the cells, use standard dev times the square root. Now, if you convert to, again, if you want to report it, you probably want to convert it to annual, because that will be easier to compare with other results. So times the square root of 260 times 100, you get something like 26. So whenever you do, well, this is part of the experience that you will gain by working with data. For example, when I look at these numbers, I will have some idea about whether this is too high or too low. So you have to bear in mind that the average SP500 volatility is about 16%. This is 26, which is pretty high. So when I notice this, I'm probably going to go back and check the sample, and I do notice that this sample, a large part of this sample is 2020, which is the COVID period, so volatility was pretty high. So 26 probably is a reasonable number. If it's a normal period, this should not be 26%. Okay, for example, if you probably you can do something like let's try this one. Standard deviation of the volatility from 2018 to 2019. So you get about 14%, which is close to 16. Okay, so that's a much more reasonable number. So you see that the high estimates of the standard deviation is all because of the 2020, okay, the COVID period. The average return, it's much more tricky, okay? So standard deviation, you kind of, it doesn't really matter which sample that you use. It's a relatively easy estimate parameter, but average return is very hard to estimate. You need a very long sample. If you only focus on this particular sample, which lasted only 4 years, SP 500 return was 14%, okay, which is pretty high. I think that's probably because it includes the rebound of the SP 500 from COVID period. If you use, for example, if you look at the return of SP 500 from 2000 and 2010 to 2010, you're going to get something like zero return, almost zero. So this number, when you estimate this number is very hard to estimate over a social sample. So I'm not going to be surprised by any estimates here. Even though we know that average SP 500 over the long term returns about 10% per year. You can do the same for the Financial Times. Just copy paste. So you can see that for this index in UK, the average return over the same period is -4%. Volatility is about 19. Volatility is close to SP 500, but the return is much lower. So this is how we compute the average return, realized return, average return, and volatility. And the last one I want to show you is to compute the correlation. In order to compute correlation, you need some add-on. Not here. Data. Directly use this one. So you're gonna have to I want to compute the correlation between the return on SP 500 and this UK index. So I'm going to copy and paste the return on SP 500. Now you have to be careful. I want to not just copy the formula, but the value of this column to the side, so I can get those exact numbers. And then you can compute the correlation. I remember that. So I come up with a correlation of 0.46. So it's positively correlated between the SP 500, the UK, the index in UK. So stock indices across the world tends to co-move together. Okay? There is a positive correlation, and so I'm not surprised about that. So, but here. So you can also plot the figure here. X-axis is the SP 500, y-axis is the Financial Times index. So you can see this 600 dots. Basically, you can see that this is basically what we call the positive correlation, because these dots are kind of close to this, the pattern looks like along this 45 degree, this positive slope line, this upward sloping line. Okay, so this is just some of you who are very familiar with Excel. This is probably very straightforward. Now we are going to talk about historical simulation. So let's focus on the idea here, because once you understand this example, you understand historical simulation. Later on, we're going to work with data. You can see that it's going to be a mess. So make sure that you understand this example. This is much more straightforward. It involves using a day-to-day change in the value of the market variable that happened to observe in the past directly way to estimate probability distribution on day T. So let's just focus on this example. Let's assume that SP 500 return were -10%, 30%, 20%, and -2%, and 5% over the last 5 years. 5 returns over the last 5 years. So those are the realized return in the last 5 years, historical return. Now, I want to ask, what can be the return of SP 500 next year? Because when you estimate VAR, you look forward, you want to estimate your risk in the future. The answer is, in historical simulation, there are millions of ways that you come up with this distribution. So this basically means, right, I want to come up with a distribution for the return of SP 500 over the next year. There are many ways to come up with the distribution. In historical simulation, this is the distribution. Answer is pretty straightforward. -10, 30, 20. So you probably noticed that these are exactly the same of those returns of the last 5 years. So the answer is -10, 30, 20, and -2 and 5 with equal probability. Which means since there are 5 scenarios, so basically, if we think about SP 500 over the next year, I'm going to tell you that there are 5 scenarios with equal probability. Each one has a probability of 20%. In these 5 scenarios, the return of SP 500 can be -10, 30, 20, -2, and 5%. And that's it. And now you may ask, how do we estimate VAR? Once you have the distribution, you can estimate VAR. So for example, we can estimate what's the 70% VAR if I loan $100 of SP 500. So if you loan 100% of SP 500, given that there are 5 scenarios for SP 500 in next year, so your loss can be, right, if SP 500 goes down by 10% in the first scenario, your loss will be $10. In the second scenario, when SP 500 goes up by 30%, your loss is going to be -$30. If SP 500 goes up by $20, your loss will be -$20. Of course, if SP 500 goes down by 2%, your loss is going to be 2 and a -5. So these negative number, basically you make money instead of suffering from a loss. Positive number means losses. How do you estimate the VAR, 70% VAR? How do you estimate expectation? So we can use 2 methods First, you can draw the cumulative loss distribution, like what we did last week. So there is minus 30, it's 5 scenarios, minus 20, minus 5, 2, and 10. So you're going to draw, there are 5 scenarios. The cumulative loss distribution will look like because each scenario has a probability of 20%. So that's going to be our cumulative loss distribution. And 70% VAR is going to be 2. What's the expected shortfall? In order to solve for the expected shortfall, you have to calculate the average loss when loss is greater than value at risk. So it's going to be 10 times the weight on loss equal to 10, which is 20, plus the loss of 2 times the weight on loss equal to the scenario loss equal to 2 is only about, you do not include all the probability, all the 20% probability, you only include the part that is greater than 70%, which is 10. And you have to divide it by the total probability when loss greater than value risk, which is about 30%. So the expected shortfall is about 7.33. So that's how you estimate the expected shortfall. So this is the approach that you can use when you use cumulative loss distribution. Now, if you use a second approach, if you don't like to draw this cumulative loss distribution function, you can use our second approach. In fact, we will use the second approach later when we do this on a spreadsheet, because there are 600 scenarios, so you don't want to draw this. So the second approach is to sort the loss from highest to lowest. Highest loss is 10, 2, minus 5, 1, minus 20, and minus 30. Each one with a probability of 20%. And you start from the highest loss, this is going to be 20%, and you want to compute the 70% VAR. So 20% is not enough. So you go down to the second highest loss, which is 20%. The total cumulative probability is 40%. So this already exceeds 30%, because 70% VAR is basically the top 30% losses. So this already exceeds 30%, so your loss, your VAR is going to be 2. Okay. So you don't have to, this is for strict. I think the most important part is this answer. Okay, if you don't understand this part, you can come to ask me during the break. Okay, the rest is just is more straightforward. Let's take a break. Loss equal to 10, probability is 20%.
Oh, because it's split equally.
Yeah.
So have you looked at the cost of this yet?
Hmm?
Have you looked at the cost of the CFA yet?
The cost to CFA?
Yeah, it's about $1,000 per level.
Oh, yeah. I have a look at it.
If you
The
ju-
cost.
If you just want to look at the practice materials, you can get
Virtual sources.
you can electronic textbooks.
Yeah.
They will give you this when you finally register, but
Mm-hmm.
if you just want to look at the stuff, you can. I think this place charges like $200 for the books.
200.
But the key is like take a lot of practice tests. You should be taking. The guy who I went through the MBA program was a finance guy. He said you should be taking a practice test every week until you can get 90% of them right. You don't need 90% to score to pass the CFA, but it's around 68 to 70% in that range. But you want to be confident you're doing the first time. You're not spending all that money every year.
Yeah.
But this is like, I think it's close to 3,000 pages if you go through all 10 boxes. So yeah, it's 2,300.
Yeah, I did watch a few video on the YouTube. They instruct how to do some different type of CFA, and I think I have a lot of type match with oracles like derivative, probability, something like that.
You're gonna go through all that stuff in here.
Yeah.
This covers all 10. There's like 10 different books that they
10 different. Yes.
and like you need to know some basic accounting too.
Yes, I did. I have it in Vietnam. Actually, all of this I have learned in Vietnam, even like calculus, math. But I learned.
How far did you go with calculus?
2, just level 2. Yeah.
So you haven't done multivariable yet?
Multivariable?
Yeah.
Yeah, I did. But everything in Vietnamese. This is my first time, so I have to translate all of my knowledge to English.
Because in the summer, you're gonna start seeing when the whole summer is essentially all Black-Scholes. That's all partial derivatives. So you're gonna be comfortable with at least the concept. It's not gonna make you do them. But,
In summer.
yeah, in the summer, the third financial modeling course. So you're gonna need to have an understanding of
Calculus 3.
at that point.
So I have to repair it on my winter break.
You could find. Are you gonna stay here over the winter? You're staying here in the winter?
Yes?
Yeah. You could find Stewart's calculus book.
Book on the library.
No, you'll find it online if you look hard enough. I probably have it.
See if I can
Go back to the library. The book they use for the most part in the States is Stewart's Calculus.
early transition.
Yeah, that just means they do log and trig focus first. Before that. This has like 15 chapters. The first 10 are
First
Calc
10?
1 and Calc 2, and from 10 to 15,
10 to 15. So
you'll have the, actually 10 to 17, you'll have the Calc 3 stuff.
okay, 10 to 15. Calculus easy.
There are free books, but this is what most courses will use, is Stewart's book.
Where? Sorry.
Most courses will use, colleges use Stewart's books.
Calculus.
And if you look hard enough, you'll find a PDF on the web for free.
You have it free?
Yeah, you can find pretty much any book on the web for free if you look hard enough.
Yes. Like this one, I found this one for
Yeah.
free. That's the 6th edition. Calculus.
What they're gonna, I'll tell you, I don't know if I signed up.
So, by the way, I love your hair. Oh, sorry, your hat. This look very cool.
I cut my hair off, so I need to keep my head a little warm. I don't pay money to cut my hair. I shave it off every 4 to 5 months.
You did yourself?
Yeah.
So,
Where'd you go back that far? What was I gonna show you? Yeah, this is our book that we're using now.
yeah.
The one you're gonna use in the spring for the normal is in here. I can't. Well, you may have to pay for it, but I can't get it I had to get it through Amazon. The other book you're gonna use this book in the second course and in the third course in
Option
the summer.
future. Derivative.
Yeah.
I see.
You're gonna go through the first. It's the same author. It's just a different book.
Yeah, picture of it. I have short memory. Thank you.
You have to go through the first 15 chapters in the equity course in the spring, and then from he does 4 chapters in the summer
Oh,
out of the same book. So
the same professor?
no, different guy. Ed Harris does
Ed Hay.
Ed Harris. He does the third course.
Oh, I'm gonna learn Ed Hay next
Ed Hay, yeah.
next week. With in our U.S. introduction, U.S. capital
Oh, you
market.
teach us some of that, yeah.
Yeah, but just 4 weeks. I have 3 professors for that course.
Yeah, I didn't have to take that course.
Yeah, because you are Darth Smith.
This is the other one that you could use for Yakov's class,
Yakov.
econometrics. What else is in here that you may want?
Linear algebra.
Yeah, at some point you probably should pick up some linear algebra if you haven't taken it. They run these courses in the summer.
Summer.
I don't know if you're going to stay here in the summer, go back to Vietnam. But if you haven't taken differential equations and linear algebra, it's a good time to take it is over the summer. You could do the Calc 3 over the summer too. If you want to stick around. I don't know what your plans are though.
So you bought all that books?
No, I've taught enough where I get books for free.
I see.
Because when you teach a course, they will give you the books to teach a course for free. And eventually, they used to just mail you hard books. And about 15 years ago, they switched. It's too expensive to print books and to mail them out to everybody who's teaching. So this company, they originally had their own distribution space. And this company said, we'll do it for you. So I can get 100 free books a year.
Wow.
These are all like for a year, but you can renew them at all.
Oh my God, you're amazing. Did you read all of that book?
No, I just keep this reference. And a lot of this is just PhD economics. Real analysis is something you would take after differential equations. It's just a real rigorous version of math. They go through calculus all over again. This is something you will need in the 4th semester class a year from now. Yeah.
Picture. Thank you. The first semester. That is agile lunch. Counterbridge funding collateral.
This is another one to look for. They use this one too in the 4th semester.
Fourth semester too.
Next fall, a year from now. I think they did this one too. Because once they teach you how to do risk in these courses, then they take to the next level. Risk when there's more than one person involved in the transaction. Like this is the kind of risk that a bank would have to.
Yeah, I focus more on the bank.
Yeah. That's this graduate level, PhD level. Same thing. I think this is one that he had in his syllabus as a backup for ours.
The backup?
If you wanted more information than what was in our book.
Ah, okay. Like go beyond to learn more.
Yeah. This is what they will probably use for differential equations here in the summer. Zill's book, that's pretty popular for undergraduates.
Investment science. I am a student. Continue. Higher education.
These are just corporate finance books if you just took a regular.
Fundamental corporate finance.
That's panel data econometrics. That's one of the other courses I'm taking this year. Like I said, I didn't say most of the syllabus. What UConn does is they take away the courses from you after a time. So even though you do that, it'll show you the courses. They close them or they take them away. Like Ed shut his course down for that took last summer. So you can't get into that. But the financials, the legal and ethical ones, you'll take this one. That's the other one in the summer.
Oh, so when you end the class, they will close your.
Yeah. So copy everything before the course ends.
Ah, I see.
And like.
Oh my God! I thought it will stay with us even after we finish it.
This place goes. Like this is the stuff for the spring. I don't know if you're registered for spring or not yet, but.
So okay, I will have to download everything if I need to store.
Yeah. Anything you want to keep, you got to download.
Yes, sir.
That's when classes start in the spring, on the 20th. So you're gonna have about 6 weeks off.
Secrets of yes.
So these two, I'll be in the same class with you.
Oh.
This is Yakov. This is a guy called Hang Bai.
Oh, I thought you joined Yakov class before.
Yeah, but Yakov teaches in the spring too.
So you just joined the
I just
first
did
one.
I just did the
model.
one you're taking now.
Ah, I see.
Because like I said, I was taking economics courses too last spring. I did econometrics too. And I did the Python course. So 3 is my limit right now. I don't want to take more than 3. I get too tired.
Yes. And you're gonna take the 5th semester.
Yeah, this is one of the 5th semester courses. If it runs. Oh, where is it? Right now, only 3 people are signed up for this course, so it might not run. That's kind of iffy to run a course with only 3 people in it.
Ah, so they're gonna like close it.
They may cancel it. I'll
Cancel
just
it.
like to have at least 8 people in the course.
Yes.
Otherwise, something worthwhile. So this may get shut down. I might have to take a different course. But these 2 already have enough people in it to run.
Yes.
You can see. I don't know if you signed up yet. We're in the spring.
University of Connecticut.
If you haven't registered, this is how you get into register too.
Yeah. I just registered my bookshelf account. Start my library. I did Yakov class this semester, but I found it like
I like Yakov.
yeah, I love his class, and I found it's like easier than what I have learned in Vietnam. In Vietnam, it's incredibly difficult.
Yeah, the class is going to be 6:30 to 9:30 next semester. Half hour later. I don't know why they're doing that, but it helps me with the traffic. Like this one already has 9 people that run it, so Yakov's class will run. We
Yeah.
just don't know which room it's going to be in yet.
To be announced.
That'll take a little bit. This other guy I haven't had yet. Well, this is hang by. This is the other one you're going to have to take. And like I said, I'll feed you the R programs. He gives them to you, but you have to modify them. And if you have trouble with modifying R, I'll give you the ones that I did. This one has 6. So this one kind of has to run because it's a required course.
Yeah.
And I think a lot of
like
you people just haven't registered for
Yeah,
it yet.
I haven't registered yet.
Again, you don't know which room it is. And the other one is
Okay.
equity.
Once you
There's already 10 in the other one.
understand
That's the required.
this example, the rest will be gradually more straightforward. So we are going to implement this idea using the data set. So let's look at our data set. Let's look at this historical simulation spreadsheet. C20 spreadsheet, historical simulation. So we still have to do some steps before we do the historical simulation. So the first 5 columns are the 4 stock indices over the sample period from 2018 to 2020, and the currencies. So when you work with the current exchange rates, you have to be careful about which currency is in the numerator and which one is in the denominator. Okay, now the first step is to convert all of them to US dollar. This is, so SP500, you don't have to convert it because it's already US. Let's work with the Financial Times Index. So you look at these exchange rates. So this exchange rate, because the British pound is in the denominator, so this basically means 1 British pound can be converted to 1.35 US dollar. Okay. So this index is in UK, so this is in British pound. So if you want to convert it to US dollar, so this is 6,515 British pound converted to US dollar. It's going to be use this number times the exchange rate. So that's why I have C5 times G5. And you have to do that for all the observations. Now for France, this is slightly different because they use euro, and in this exchange rate, US dollar is the denominator, and Europe is in the numerator. Okay. So therefore, when you convert it, because this index is in euro, so you convert to the US, you have to use this index divided by this exchange rate, because this exchange rate basically means that 1 US dollar equals to a 0.5854 euro. So you have to use this index level divided by this exchange rates to get this index in US dollar. Same for the Japanese index. Use Nikkei index divided by the yen US dollar exchange rates. 1 US dollar is about 109 yen. Now you have all the currencies in, you have all the indices in US dollar. you have to compute the daily return, as we just did, for SP 500 and the Financial Times Index. So you're gonna compute, you have to compute the return on SP 500 and the return of this French index as well as Japanese index. So as you can imagine, this return includes two parts. First part is gonna be the changes in the index itself. The second part is due to the fluctuation in exchange rates. So that's part of the risk of investing in foreign stocks. So exposed to not just stock risk, but also the exchange rate risk. So for all these three indices, you're gonna have exchange rate, you're gonna expose to exchange rate risk. So you have these four, now you have all the returns in US dollar. Now we can do over this whole sample period. There are, let me see, there are about 500 observations. So we have, start from 6 up to 505. So there are 500 observations. We are going to do the historical simulation. So this is the key step, historical simulation, which is this tab, this column, all of this. So what are we going to do? Let me just remind you the idea here. So we have 5 observations, 5 years, five returns, and I'm trying to create a distribution of returns for the next year. The distribution will be the five scenarios based on the last 5 years with equal probability. Now we have 500 observations. They're not annual, they're not yearly data, but they are daily data, but doesn't matter. Okay, we have 500 daily observations in the past. So what I'm going to do is I'm going to create 500 scenarios for tomorrow based on that 500 returns in the past in my sample. So that's exactly what I'm going to do. So let's pretend that we are at the end of the sample. At the end, it is in 2020, July 8th. Okay. Now the market is closed. I'm doing some risk analysis, and I'm trying to analyze the potential risk of this portfolio for 9th, tomorrow. So I will start with this for the level, the dollar level of these 4 indices, dollar value level of these 4 indices at the end of the sample. So these 4 numbers. That's basically the closing price. Let's assume that today is July 9, 2020. So that those 4 numbers are the closing price of this dollar price of these 4 indices today. And I try to estimate, I want to estimate my VAR for tomorrow. Therefore, I'm going to create 500 scenarios based on the 500 returns that I have in the data. So let's start with the first one. Let's look at this row. This is my first observation. First scenario for tomorrow. So in the first scenario, I'm going to assume that SP 500 return is going to be the same as the return of SP 500 in the first observation of my sample, which is a daily return back in 2018. So I'm gonna use that return. I'm gonna compute the value of SP 500 by the end of tomorrow based on that return. So this is how you're gonna compute it. So this is the price of the SP 500 at the end of today times the return plus 1. You're gonna get the SP 500 tomorrow, by the end of tomorrow. Same for all these three indexes, three other indices. You use the second day return, the first day return for all these three. Now I'm going to look at the portfolio. On my slides, I'm going to show you the portfolio. So this is my portfolio. I have 4,000 in SP 500, 3,000 in Financial Times, 1,000 in French index, and 2,000 in Nikkei. So total of 10,000. Hope that's clear. If you cannot see it very clear, you can look at your own laptop. Just look at this particular cell. So I have 4,000 in SP 500. This is going to be the return of SP 500 under the first scenario. 3,000 in Financial Times. This is going to be the return of Financial Times index in the first scenario. 1,000 in French index, return of that index. 2,000 in Nikkei index, return of that index in the first scenario. So now, under the first scenario, the value of my portfolio value will be, my portfolio value by the end of tomorrow will be this number. Therefore, I'm going to make a profit of $64, which is a minus $64 loss. That's the first scenario. And I'm going to create the second scenario, too, using the second observation. Same as what I did for the first scenario. Okay, so if you use the second observation, second return, to create all this for all the four indices, you can compute the portfolio value too. Okay, in the second scenario, you can see that I still start with, right? My portfolio is $4,000 in SP 500, 3,000 in French in this UK index, and 1,000 in French and 2,000 in Japan. So that's going to remain the same. The difference is that the returns of these indices in the second scenario will be different from the first scenario. So these returns are different. And I'm going to make $66, and hence my loss is minus 66. So then the rest is just repeat what I did for the first two and for this. Then you're going to create 500 scenarios. If you know Excel well, if you have a good Excel skills, you probably notice that I write this, I add this dollar signs, those kind of things. This is just some tricks in Excel. These dollar signs, I'm going to fix that number when you add a dollar sign in front of 5, for example. This number will be fixed when you drag the lower right corner of this. Okay, this is just a trick in Excel, or you just double click in the lower right corner. You apply the formula for all these 500 scenarios. And then we have 500 scenarios based on the 500 observations in the past. And we're going to have 500 losses. That's the most important part. We have 500 losses. Once you have 500 losses, right, we're going to assign equal probability to each scenario. What's the probability of each scenario?
0.02?
0.2%.
Yeah.
0.2%, thank you. So they are equal likely. So then you have a distribution. Of course, you don't want to draw the cumulative distribution function. That's going to be 500 points there. So I'm going to use the second approach. In the second approach, you can copy, this is what I did. You can copy, select all the losses, all the 500 losses, copy, probably many other ways you can do it, but you can copy by value instead of the formula, copy by value. And you're going to sort, go to the tab of data. There's this, you can sort the value. From the largest to the smallest. So this is exactly the sorted losses from the highest to lowest. Now I want to compute the 99% VAR. Given that each scenario has a probability of 0.2%, 99% VAR basically means you want to estimate the top 1% losses. Top 1% given each scenario is 0.2%, so that's the top 5 scenarios. Top 5 losses. Okay? So that number is going to be your 99% VAR. Because you have 500 scenarios, 1% means top 5. You have the VAR, and you can estimate the expected shortfall. So expected shortfall is the average loss. By definition, expected shortfall is the average loss when loss greater than value at risk. So you're going to take a simple average of the 4 losses, given that they are equal likely, so you can take simple average. Which is called average of these 4 cells. You get the expected shortfall. So now this is the historical simulation. And we're going to talk about some extensions. What does this number mean, right? So 99% chance that your loss will be less than $422. Your expected loss, if loss greater than 40 to 422, will be 731. So that's the, I think I call it baseline, base case of the, now, well, if you like look at the distribution, this is going to be the loss distribution over that 500 losses. So you do a histogram of that 500 losses, you're going to get this distribution. If you really like to do some kind of cumulative loss distribution, right? Because I have 500 losses now. If you really plot, I plotted it using a computer, you can see that this is going to be a very smooth curve instead of that function. It's going to be very smooth. But this is the value, the cumulative loss distribution. You can compute that too. Given that 500 losses with equal probabilities. So if you would like to compute 10-day VAR, you just use square root of 10 times the 1-day VAR or expected shortfall. So that's the standard historical simulation. Stressed VAR, stressed expected shortfall. One drawback of the previous approach is that maybe underestimate VAR in the case that most recent day may be a period of low volatility. The volatility increases tomorrow because you basically use, you can think about that over the lab, right? You can think about like before COVID, you used the data before COVID, before February 2020 to estimate VAR, and suddenly there's a big change to the market, the volatility spikes, the risk suddenly increased a lot. Therefore, if you use those data before COVID, you underestimate the risk during the COVID period. So that's what we mean here. So that's an issue. If you use a sample with relatively lower risk, you're probably going to underestimate the risk, the VAR. Instead of based on calculation movement market over the last 10 days, you can base calculation on movement during a specific day in the past. It's very, very bad for the current portfolio. And you estimate that VAR, that's called stress VAR, stress ES. These are mainly used by regulators. Now we're going to talk about some extensions. We basically, when we use the previous approach, when we use the historical simulation, we have this assumption actually underlying it, is that we assume that the data provide a good guidance about the risk in the future, but that's not always guaranteed. Okay? That's an issue. So this is not always the case. This is why regulators introduced this stress VAR and ES. Now we're going to talk about some more extensions. So first one is the weighting of observation. So if you go back to the sample, our sample starts in 2018 and ends in the summer of 2020. If you follow the market, you probably know that the market became very volatile, very risky after COVID hit. So if you use those data observations in 2018 to estimate the risk in the summer of 2020, you may underestimate the risk, the VAR. The reason is because remember that there is a key assumption, there is another assumption that we have here is that we create these 500 scenarios, we use those observations back in 2018 to create the first observation, first scenario, and we assign equal probability to all of them. We probably should not do that. We probably should assign a little bit lower probability to those scenarios created using the data in 2018 and put more weights in those observations in 2020. So that's the idea. So, because the recent past is more informative about future than the distant past. Okay? So therefore we're gonna put more weights on those recent past than the distant past. So we're gonna replace that assumption that we're gonna put the equal weights across all the observations in the sample. And we let the weight, as they decline exponentially as we go back in time, the weight, and of course now you need a function, right? The idea is that it put more weights in the recent past. But to implement it, you need a function. So this is a standard function people use. Okay. Lambda is a parameter. I think it's like, it's 0.97 or 0.9. We can assign number. Lambda is a number that's close to 1. N is the total number of observations. I is the index for a particular observation. So if you plot that, most important is that plot this function as a function of number of days ago You can see that yesterday, for the observation yesterday, you put the highest weight, and for the observation 500 days ago, the weight is much lower. And this is decreasing. So the longer in the past, the weight is going to be lower. So we're going to put different weight across those scenarios created using different observations. And this function is chosen because the sum of the weights equals to 1. So you can think about these weights as like the probability of each scenario. So let's look at how I implement it. So you can look at the exponential weight, the tab called the exponential weight. How did I do this? So this is how I do it. I'm gonna copy. So I'm gonna start with this standard historical simulation. I copy the column, the number of the observations, and the loss. We'll have to select both columns. Let me try this. Okay, these two. Cannot do that.
Merge the row.
Yeah, I just don't want to do it. I have to. Okay, I'll just select all of them. Okay. If you press Control key, you can select both of them, both these two columns, and then you can paste by value. I think that's important. Okay, so this is the first step, and then you will have to sort, select the losses, all these 500 losses. You will sort from highest lowest. And now you need to click expand selection, because I want to, when I sort this column, I want these in this scenario number to be sorted according to the losses as well. So you can see. Weird. How to sort the first. I want to include the first. Maybe I should Okay. Now, what I did is that I sorted all the scenarios according to their losses from highest to lowest, and this number, scenario number, is going to be sorted too, but it's not going to be sorted by the number, then it's going to be sorted based on the losses, the corresponding losses. Okay? So I obtain column A and B now. Now the third one is to now I have to compute the weight. I want to keep the scenario number because this scenario number is going to keep track the number of days in my sample. So I'm going to need that scenario number to compute the weight, because now I have different weights for different scenarios. So I'm going to use that formula. You can see that my lambda equals to 0.995. This is the number of observation in my sample. The higher the number, the more recent this observation is. So I can compute basically I compute the probability of each scenarios in my sample using the formula. And if you want to double check, you can take sum of all these weights. It should be equal to 1. Okay, you can see that the probability, you can think about these as the probability of each scenarios, the sum of those probability equals 1. And then you can start to compute the cumulative weight, cumulative probability. Okay, start with the 0. Well, if you don't like to do it, if you find this, you can do this way or another way. So you can use M1 plus L2. You will get the cumulative probability when you drag this. Okay, basically each time you will add the new, for each row it will add the new probability. So if you take, you can see that this is going to be the cumulative probability. If you look at the 1%, that's going to be your 1%. Okay. So your value at risk is going to be 643. Not the top 5, but the top 3, because this is not equal weighted. So this slides basically show the top 5 scenarios when you have different weights. You can see that the value at risk is 653. And the ES is a little bit more complicated because now you don't have equal weights. So when you take the average of losses, you have to consider different probability. So the 1 day 99 ES is going to be the first one, the first loss times the probability plus the second one times its probability. The third one times, now you have to be careful here, is that you only include the top 1%. So you're going to use 1% minus the probability of the highest loss and minus the probability of the second highest loss. And that's going to be the probability of the third losses. And you're going to divide it by 1%. That's going to be your 99% expected. Okay, so basically you take not a simple average, but some kind of weighted average according to the weights.
So is your lambda based on this was a 4-sample portfolio?
Lambda?
Does lambda vary by the portfolio number of indexes that you used? See how it says application to a 4-index
No,
portfolio?
lambda is a constant.
Yeah, but does it change if it was a 3-index portfolio? Or,
No, I don't think you change that if
Okay.
there's 3 index or 5. You can use 0.995 for any number of indices, any portfolio. But this number is just an example. I guess in practice they will give you a number. But it's going to be a number close to 1. So let's look at the results. Let's compare the results. So that's going to give us more intuition here. So baseline, the previous, in the baseline, the basic historical simulation, we got a BAR which is 422. Put all weights in the recent past, you can see that the VAR estimates is much higher, 653. Expect shortfall in the baseline is 731. If you put more weights in the recent past, you're gonna get about 800. Which one is more reasonable? Obviously the second one, because this one is a better estimates, because you are trying to estimate the VAR in 2020. Which is a very volatile year, very risky year. So, but the takeaway I think you should have is that this estimates is going to vary a lot. You can see that this is different from solving a model where you're going to get an exact number when you work with data. No, it's an art. So you can come up with very different numbers, okay, using different approach. You can see that you use different approach, you're going to get a very different number. Which number makes more sense? You have to gain some experience to be able to figure that out. Okay, so but right, so different approach is going to give you different results. Basically. We will see another one. It's called volatility risk. So we want to adjust for volatility risk, the changes in volatility risk. Because you can imagine if the market is more volatile, then your value risk is going to be higher. If volatility is less, market is less volatile, your value risk is going to be low. When volatility is high, you are in a very risky environment, so it's not surprising that your value risk is higher. So we want to adjust for volatility risk. In order to adjust for volatility risk, you need a measure for volatility, a time varying volatility. Oh, okay, let's look at the idea here before we jump to the estimation. So, how do we adjust for volatility? Let's look at this example. So S&P 500 volatility was 10% in June. The return was minus 1% on June 15. Now I want to use that data observation to create a scenario for tomorrow, let's say tomorrow. And let's assume that by the end of the day, S&P 500 volatility, VIX index is 20%. How do I create a scenario based on the return on June 15, with and without adjustment for volatility? Without the adjustment for volatility, right? So you basically, in this scenario that you created, S&P 500 is going to be minus 1%. But what if I want to adjust for volatility, the changes in volatility? How do you create this scenario?
To do simulation?
This is simulation.
Is it the volatility now?
Exactly. Okay, so you're gonna do minus 2. Use minus 2. So you want want to adjust for volatility, and the return was -1%. When volatility estimated is 10%, and now volatility is 20%. Which means your risk is twice as the risk in June, back in June. So if your risk is twice the risk back in June, when you create a scenario, it's called R delta, you're gonna use -1 times 2. Okay? You're gonna increase the risk by 2, by a factor of 2. Now this is the case that this is exactly 2%, but if we, let's call this V0 and this is V1, well, let's call it sigma. It is sigma. In general, right, so you're gonna have this formula. So you use -1% divided by the volatility in June times the volatility, the current volatility. You use this ratio to adjust for volatility when you create the scenario. That's how you adjust for volatility risk, the time varying volatility. Now, of course, you will need a measure of volatility. The standard one for SP 500, we have a standard index called VIX index that can be used as a volatility measure, a time varying volatility measure. However, in this data set, we do not just have SP 500, we have Financial Times Index, French, and the Japanese index. So we cannot use VIX for the other 3 indices. Therefore, we need a measure, create our own measure of volatility. So here we're gonna use a simple, pretty straightforward model to estimate volatility. It's called exponential weighted moving average for volatility. So this is the model. This is the equation. What we can do is basically there's a lambda, again it's a parameter, okay? It's 0.94. Okay? And sigma n-1 is the volatility measure yesterday. Un-1 is the daily return of the stock on day n-1 yesterday. And based on that, you can compute, based on this equation, you can compute the volatility on day n. And you can keep doing that, okay, for each day in your sample. You can compute the volatility index. This is called exponential weighted moving average. It's just a volatility measure, okay? So it's nothing fancy. So we just gonna, what we're gonna do is we are not trying to fully understand this equation. Instead, we're just gonna use it in our expression. So now you can look at the tab called time varying vol exponential weighted moving average. We're going to estimate the volatility. For SP 500, let's start with SP 500. So B is SP 500, return of SP 500. And in order to use that formula, we need the initial value of volatility. There is no unique answer for the initial value. You can try any initial value. Here, I'm going to use the total variance of the entire sample as the initial value. Okay, it's just going to be variance of all the returns. I'm going to get the initial value. And then starting from the second observation, you can use lambda is 0.94. You can use the previous, this is the sigma n minus 1 square. Okay, this is the variance, so it's the sigma square times d phi plus 1 minus lambda times the return in the previous day to the square. You can compute the volatility, the variance on May 11. And you can keep doing that for every day in your sample. You can see that this is basically updating the volatility based on this equation. You can apply that to all the days, daily observations. You can get time varying volatility measure. And then you can take the square root of it. You can get the volatility. So the D is the variance and E is the standard deviation, which is the volatility. Now if you so if you plot the volatility as over time, over dates, you will get this curve. You will get this time series, this line. So you can see that basically, no surprise that in March 2020, there's a spike of volatility because of COVID. Then the volatility starts to decrease. So this is a time varying volatility. Now, we can talk a little bit about the initial value. This is the initial value. The initial value is going to matter a little bit because, as I said, the initial value can be arbitrary. There is no unique answer, correct answer to it. So you can use the total variance. But if, for example, if you substitute it with maybe let's use 0.01. I think I should use probably 0, maybe. So you can see 0 is a very extreme number that I use. When you use 0 as the initial value, it doesn't really change this line much other than the first half year, first 6 months. So if you want to look at it again, this is the one that I use the total variance of the sample. Now if I set it to be 0, it's just the first, probably first half year that's going to be affected. So this initial value, there's no good answer, correct answer, so you can, theoretically speaking, you can use any number you want as long as it's not too crazy. But the rest of it is not going to be impacted, so that's good news. Some cases they're probably going to recommend you just remove this part. Instead of using this part, remove that part when you estimate VAR, because that part depends on the initial value. But here we're going to keep using. Okay, so the reason that the initial value doesn't really matter is because of these exponential weights. So you basically, that's going to kill the initial value in the long term. So anyway, so we obtain a volatility measure, and then we can do quality, the corrected DAR. Let's take a break. Sorry.
I have a look. Some of the books very expensive. Definitely have to find the free one.
Oh yeah. If you need calculus, have you ever seen this guy?
No, no.
He's the
Professor-
best online calculus teacher I've ever seen. He's all the major courses too.
Oh, I love you too.
So he does Calc 1, Calc 2, Calc 3 differential equations, college algebra,
Leon. Yeah. Okay, I found it.
stats. He never did linear algebra. He was supposed to do differential equations too.
Mm-hmm.
He did these like 10 and 7 years ago. But he had a kid die on him and it kind of messed him up. He had like an infant die in like the first year of life or something like that. So he stopped posting videos after that. But, so you can understand that. But nobody has ever explained to put it. There were people that say they didn't even go to class, they just watched his videos and they got named courses.
Wow.
That's how good of a teacher he is.
Wow. Yeah, a good teacher is to explain how to like a kid can understand it easily.
This stuff you're seeing right here, you're going to just spend a whole month on it next semester. In the financial modeling too.
This one?
Yeah, this time series volatility.
But we're gonna use our other program,
You're going to use R.
R.
Hang by uses R.
It's easier to use R or Excel.
Well, you can see Excel gets funny at times. R is made to handle the big numbers and stuff like that. Because you're going to use a 10-year history of the S&P 500.
Yeah. Professor Leon.
Now, do you use any commercial software? Because you can get software from Yukon. I don't know how much you use.
When you post your video on YouTube, do they like limit your video or the length of video?
No.
Oh.
I think there is a limit, but it's long. Because one actually recorded in something I recorded in the past was recorded in slow motion, which means it's like 250 frames a second. So the video was like 17 hours long, and YouTube wouldn't do that.
Yeah, that's YouTube is the great place to store our video, especially the heavy one. Save storage.
So you from UConn, because you're a student here, you can get software through the university. Most is for free.
Oh wow!
Like,
Oh my god, I haven't known this.
you ever use
before.
Mathematica?
Not yet. MATLAB.
This is the best symbolic derivative calculator known to man.
Oh.
MATLAB is a good math program, but Python can kind of do everything they can do at this point. This is an add-on to Excel. Power BI is a presentation program that's made for business analytics. If you're gonna do stats and stuff, you use Minitab SAS or SPSS. This one here. Wolfram Alpha Pro is something that they usually make you pay to use on the web. It's just an all-around math question answer thing. Statistics again. Economics uses this a lot for their modeling. But you get all this for free. You just have to sign in with your net ID and stuff.
Where you use for Python? One of my friends, they use like Google Apps, and yeah, he instruct us to download another program.
Python, I use Anaconda. Which
yeah, Anaconda,
I think I put this on here. Come on, open up. I'm not a big fan of the Mac, but I have them. Because the battery will last on it. The Windows laptops, the battery is dying by the time we get ready to get out of here. Stop. Not now.
I saw you have like Final Cut Pro. Maybe you gotta like.
That came with the Mac, yeah.
You have to bought it, right? You have to.
But when you buy it with a brand new Mac, it's like 1/10 the cost of if you buy it privately. That's why you do it when you buy a new Mac.
Oh. Wow.
Get out of the
I
way.
bought my Mac in Vietnam, but I don't have it. I have to pay like $400 to get it.
Well, you'll get if you buy something new from Apple here, go to education.apple. It's called the Education Store. I'm not sure. I think it's education.apple.com, whatever. And you get a discounted price because you're a student here. And once you go through that, you'll get the whole Final. It's not just Final Cut Pro. You get the whole suite, all 5 applications, for $200 when you buy a new Mac.
Wow.
Oh no.
So that's why I always order it. Jupyter is what I use to do Python coding.
Wow, a lot of new things. Oh my god, amazing. Software.
And then you just go File, New, Notebook.
Student.
And this is what you're going to put all of your.
Python, Coda, Anaconda, Select.
And you just type in the cells. You can do it the whole program in a cell, or you can just have a bunch of cells in a row.
I see.
This is. This is what you use for Python. This is what Yakov had trouble with. He just tried to do it with Spider, and Spider does not work good. There is economics runs a course in Python in the spring. But like I said, because of the way this program works, they would charge you for it. You wouldn't get it for free. But if you were in economics, you could just take it as a fourth course. But they don't do that here. But there's a lot of tutorials on Python just on YouTube. That if you really want to learn it, you can do it. Data Camp is what they use to teach it. I don't know if you can get. If they make a course in it, you can use it for free. I don't know if you can use it just as a student for free without paying for it. At UNH, University of New Haven, we were able to use it for free just as a student. I don't know if it has the same relationship
With who?
I went to a college about 30 miles down the road up Route 95.
Oh, I see.
At the University of New Haven.
New Haven.
Yeah.
Yale?
No, Yale. No, it's called the University of New Haven, but it is in New Haven, like Yale. It's right at the border.
In the same city. It's in the same city.
Yeah, it's right at the West Haven, New Haven border.
Yes.
Google Maps.
It's very funny that when I did like Google in like how to say American names, instruct me to say we have to say call them by their last name, blah 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 blah.
No, we don't. Everybody in the States is the first name.
Yeah, new thing to learn.
See, we're right here down here in Connecticut. They put a star there because that's where I live. But you've ever been up to Stores? Stores is up here.
Yeah, I'm going to store this weekend to join their investment banking day. They're gonna invite some professional from like Morgan Stanley and blah 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 other firm to talk to students.
It's up there. It's gonna be about a 2-hour drive from here. But are they gonna run a bus for you?
Yeah, I gonna have a bus.
Yeah.
It's take me like 4 hours.
This is the UConn campus.
Yes. Have you ever been there?
Oh yeah. I did undergraduate chemical engineering there in the 1980s, graduate chemical engineering in the 2000s up there.
Wow. How many degrees you have?
I think I'm working on 9 or 10 at this point.
Oh my god. Oh my god.
I'm what's called the lifetime student.
Yeah, lifetime student. Long life learner. Wow, 9 or 10.
Where's satellite? They usually show you satellite. Maybe because
But to be honest, you inspiring me a lot in my learning journey.
Yeah, the business school is right around here, which is probably where you're gonna go. Right around there is the business school. So they'll probably drop you off in front of the business school. It's about a mile from end to end. This is where the dorm I lived in as an undergraduate was in North Campus.
Do you have any suggestion that where should I visit the on-store campus?
Just
Cool
walk,
place?
just walk around.
Walk around. Okay.
Go to the library, see what the library is.
I heard my friend said that they have a amazing ice cream at store campus.
That's
I
at the
must
dairy
try.
barn. The dairy barn is up here.
Dairy
It's probably about a half mile from where you're going to be.
for
Okay,
the event.
So,
Now we have the time varying volatility.
Amazing.
So let's look at the next tab. It's called volatility corrected. So there are several groups of columns. So these are from A to E. These are copied from historical simulation, I believe. So we have this. And then we also copied the daily return in US dollar. Okay, so we have the daily return of these 4 indices in US dollar. Now we need to compute the variance and volatility measure. So as you see, why do I have Dow Jones? So as the first observation, first the variance, the initial value of the variance, I'm going to use the whole sample variance. And starting from the second one, I'm going to use the formula of the exponential weighted moving average. Volatility. So I can compute the time varying volatility. And I can also construct the volatility measure for these other 3 indices. So I have the variance for 5 indices. I take the square root of all of them, get a volatility. You can actually look at it. So this is kind of like the volatility measure, the volatility of these 4 stock indices. You can see that all of them spiked during the COVID period. Okay. So and there's a pretty strong correlation across the volatility as well. In fact, if I remember correctly, the correlation in volatility is across countries even higher than the index itself. Okay. Basically means that, you know, in this globalized world, that this uncertainty, the volatility is a measure of uncertainty. So this uncertainty is gonna be across the world usually, impact across the world. So impact all the countries. So that's why we have these correlated volatility. Now, if you have all these, now you can start to do the historical simulation. This is the key part of historical simulation. So once again, I'm going to start to create 500 scenarios based on my sample, which has 500 observations. So I'm gonna start with the first scenario. First scenario is gonna be based on the first observation in the data. Let's look at SP500. So what I did here is G8 divided by Q8. So you can see that Q8 is the volatility of SP500 in the first observation. G8, so I'm going to use this formula. Sigma 0 is going to be the volatility corresponds to this -1 observation. And remember that this formula that we create, so the idea of volatility adjustment, right? This is an observation in the past. This is the volatility on that day. And this is my current volatility. So I'm going to use the return in the past on that particular day divided by the volatility on that day times the current volatility in order to create a return for the scenario. This scenario. So Q8 is my sigma 0. G8 is my sigma 1. Q508 is the return, -1%. Okay. And then times W7, which is the current level of SP500. Now, what is you may ask, what is G8? Let's look at G8. Oh, sorry. G8 is the return, not the volatility. Okay, G8 is this daily return. So daily return divided by the volatility on that observation times the Q508. Now, what is the Q508? That's the volatility for tomorrow. That's my predicted volatility for tomorrow. This number. This is an advantage of the exponential weighted moving average. Okay. You can forecast the volatility tomorrow based on that model. So if you look at this model, right, this is the current volatility, and this is the return today. And if I plug into this equation, I can compute forecast volatility tomorrow. So that's exactly what I did. So you can go for one more day when you compute the variance based on exponential moving average. You compute for one more day, you're going to get a volatility forecast for tomorrow for all these 4 indices. And this is basically the forecast volatility tomorrow. And I'm going to use that forecast volatility tomorrow to adjust for volatility, to adjust the volatility for when I create this scenario. Okay. That's what Q508 is. That is the Q508. Same for these 4 other indices. So I'm going to have 4 other indices after correct for volatility. And now the rest is the same as the historical simulation. You use these returns and the weight, the dollar amount on each index is 4,000 in SP500, 3,000 in Financial Times, 1,000 in this French index, 2,000 in Japanese index. So you can compute the value of your portfolio in the first scenario by the end of tomorrow. And you get a loss of -71. You can do that for 500 times. You're going to get losses after adjust for volatility. Now again, we're going to copy and paste all this. I have 500 losses. I'm going to copy paste that by value. And I'm gonna sort from highest to lowest. That's basically this column. And now you don't even, now again, you don't need to put different weights across this observation, these scenarios. We're gonna put equal weight because we have already corrected for time varying volatility. We have already corrected for variance, the volatility risk, the changes in volatility. So again, 99% VAR is the top 5, the 5th losses, highest losses, and the ES is just gonna be the average of the 4 losses, which are higher than the variance. So that's the historical simulation after adjust for volatility. Now we can compare some numbers too. Do this here. So if you look at the baseline case, the VAR is 99% VAR is about 420. Now, if you correct for volatility, the VAR is 566, which is significantly higher. Now we can also compare with the exponential weighted estimates. Which is 653. So you can see that after correct for volatility, the value at risk is higher. The estimate for value at risk is higher than the simple case, the base case. So the reason is, again, when you look at it, when you do the data work, you have to keep thinking and asking yourself whether this number makes sense to you, and why do we have higher or lower estimates. Sometimes you're going to make some very easy, very simple mistakes. The reason is, again, because after correct for volatility, the estimated value risk is high, significantly higher than the base case is that at the end of this sample, you can see the volatility, even though it's less than this peak of the volatility in March, volatility is still pretty high compared to most of the sample. So when you correct for volatility, actually, you increase the risk from the base case. But of course, adjust for volatility makes more sense because this is a relatively higher risky environment. If you estimate VAR should be higher, right? You think about this, right? These points, when you're using the data points here to create a scenario for this environment, obviously you should increase the risk, corresponding risk, when you create scenarios for this environment when volatility is much higher. So you should adjust for volatility. So let's adjust for volatility. The last one method is another approach to adjust for volatility. You don't adjust for volatility. It's a simple approach. You don't adjust for volatility for each indices. Instead of that, you adjust for volatility for your whole portfolio. So you can look at my spreadsheet. Loss correct for volatility. This is, so I started from, I don't correct for I don't create volatility index for each stock index. Okay, so instead I just gonna use the base historical simulation so I'm going to use this scenario number and the loss. I'm going to copy these two columns. So that's going to correspond to my A and C. Okay? So I start from there, where I'm going to have law using the base historical simulation without any adjustments. I'm going to start from there, and I'm going to construct volatility, time variant volatility measured using the exponential weighted moving average, but I'm going to apply that directly to my loss. Okay, so I start with the variance of the whole sample of the loss, and I'm going to use this formula to update my variance on each observation. Same formula. So I'm going to have a variance ratio, and then I take the square root of that variance. I'm going to get the standard deviation. And I compute standard deviation ratio, which is for each observation. It's basically the sigma 1 over sigma 0, where sigma 0 are the standard deviation of each observation. And sigma 1 is the forecast volatility for tomorrow. So, and then I'm going to use this standard deviation to adjust for loss for each scenario. Loss divided by the standard deviation for each scenario and times the forecast volatility for tomorrow. And I have a bunch of adjusted losses, and then I can copy paste all these 500 losses by value. And then I can sort from highest to lowest. Not gonna extend it. Now you can see I can get column I, and the 99% value of risk is going to be the top 5, the 5th highest loss. Because I've already corrected for volatility, I'm going to assume equal probability across all these scenarios. 517, and the expected for is going to be the average of the top 4. If you compare this with this more complicated method, you're gonna get that. You're gonna find that they are close, not exactly the same, but close to this estimate. Okay. So that's another way to correct for volatility risk. Okay, so I guess that's the historical simulation. If there's anything else. Then there's this bootstrap method that you may ask, right? You get an estimate of VAR and expected for using historical simulation. You may ask if I can get instead of a point estimates, can I get a range, which is what we call confidence interval, like at 95% sure that my VAR is going to be in a certain range. You can do that. It's called bootstrap method. It's different from constructing the yield curve with fixed income. So this is just a statistical method. You basically try to create some artificial sample by withdraw random numbers from your existing sample, and then based on this random samples, you create a lot of artificial random samples, and using the same method, the historical simulation for each sample to compute the value at risk for each sample. And then because you have a lot of samples, so you're going to have a lot of value and risk estimates. Once you have a lot of them, for example, you can have 1,000 VAR estimates of your VAR. You can draw a distribution. Once you draw a distribution, you can come up with a confidence. So that's just the statistical method. It's called bootstrap. Okay, I'm gonna stop here. So next time we will talk about Basel 1-2. And the homework will be due next week.
Before the class?
Before the class?
Yeah, yeah.
Yeah, I'll do that.
No, thank you.
I need to look at the
Okay.
plus.
Like probably like Saturday, Sunday. After the exam.
It should be 20%. Yeah, and then 2 times 10%. Yeah, you only include